Hello, this is Alex Howe with the Science Meets Fiction Exoplanets review for March of 2022. It took a while, but I finally did get the video done. I've been reorganizing my workload this month, so next month's video should be easier. Although it will still be delayed a bit because in the first week of May, I will be at the Exoplanets 4 conference in Las Vegas, ironically to present my research about brown dwarfs. Long story. I may do a special edition for that, but I feel like I'm not the best person to do conference coverage. For something that fast-paced, you'll probably have better luck following the Exo4 hashtag on Twitter. There are several astronomers who do really good live tweets of these conferences, so you might want to check them out. Anyway, let's get started looking at the latest developments in exoplanet science in March. And of course, the biggest news from last month is that we officially hit 5,000 confirmed exoplanets, at least by NASA's count. The first exoplanet was actually discovered in 1988, around Gamma Cephei, but it wasn't confirmed until 2003. The first exoplanets were confirmed in 1992, but even those were these weird pulsar planets, which don't exactly count as the usual kind of planets. I'll talk more about those later on. So we usually say the first exoplanet discovered was 51 Pegasi b in 1995, which was the first exoplanet confirmed to be orbiting a normal main sequence star. And since then, the number of known exoplanets has grown exponentially, as we've found better and better ways of detecting them. First by radial velocities, and then with the launch of the Kepler and TESS satellites, mostly by transits. And in March, we finally passed 5,000 confirmed planets. So that's a pretty big milestone. Another interesting paper that came out last month was about the definition of an exoplanet, or rather the International Astronomical Union's working definition of an exoplanet. You may remember back in 2006, when Pluto was demoted from a planet to a dwarf planet by the IAU, when they finally hammered out the definition of a planet in our solar system. But exoplanets have different considerations, and still don't have a formal definition. Until recently, they were classified from a working definition published all the way back in 2003. But the IAU recently updated that working definition to define them more precisely. Now, the main parts of the definition are the ones you may be familiar with. Planets must be orbiting a star or brown dwarf, and must be smaller than the deuterium-burning mass limit, which is about 13 Jupiter masses, so that they never undergo nuclear fusion. Now, this definition excludes free-floating planets, sometimes called rogue planets, that are not orbiting a star. We usually say free-floating planets, even in the field of astronomy. But officially, at least by the working definition, they're not really planets, but rather sub-brown dwarfs. But the new definition addressed a different issue, which is binaries. What happens if you have a binary of a brown dwarf and a planetary mass object that are pretty close in mass, maybe even within a factor of 2 in mass? It seems like that shouldn't really be a star and planet relationship, but more of a binary brown dwarf relationship, even though one of them isn't technically a brown dwarf. So the IAU decided to somewhat arbitrarily set a limit that you have a binary object when the L4 and L5 Lagrange points are no longer stable. For a planet orbiting the Sun or a moon orbiting a planet, the points in its orbit 60 degrees ahead of it and behind it are Lagrange points where you can park a spacecraft and it'll stay there. It'll wobble back and forth, but it'll stay pretty close to the same place. But if the star and planet are sufficiently close in mass, those are not stable points, and spacecraft parked there will wander away over time. And that mass ratio is actually very precisely defined mathematically, and it happens to be about 1/25th. So if a brown dwarf or even a small star is orbited by planetary mass object larger than 1/25th of its mass, that's considered a binary. And the working definition doesn't address this, but I actually think this would be a very good definition for a binary planet. We sometimes hear about double planets in science fiction and even in astronomy occasionally, but there's not really a good definition of it. The most common definitions have to do with the center of gravity of the system, and that can change over time. But a fixed mass ratio criterion would work pretty well, and the 1/25th value is pretty intuitive. So if you have the Earth-Moon system, where the mass ratio is 1:81, that's not a double planet. For the Pluto-Charon system, where the mass ratio is about 10:1, it is a double planet, or rather double dwarf planet. Of course, this still leaves some ambiguities. Exo-Moon hunter David Kipping pointed out that if you have this scenario, it's not clear what to call it. If you have a free-floating 5 Jupiter mass object, that's a sub-brown dwarf. And if it has a planet-sized object orbiting it that is smaller than 1/25th of its mass, it's not clear what that should be called. It's not a planet because it doesn't orbit a star or brown dwarf, and it doesn't seem like it should be a sub-brown dwarf either because it's not free-floating. So is it a moon? The working definition doesn't really address that. So there's certainly still work to be done on that front. Now let's get into the actual exoplanet discoveries from last month. This first paper talks about the discovery of 2 planets, TOI 1670b and c. And these planets are not that remarkable in themselves, but they are interesting from a formation perspective, because we have an inner sub-Neptune with an outer warm Jupiter, and that does not match the usual formation models. If you go back to the video for January, you'll see that I talked about how the distribution of planets shows evidence that warm Jupiters and hot Jupiters formed by eccentric migration. That is, they were most likely kicked into an eccentric orbit by a close encounter with another planet, and then circularized to a smaller orbit later. But not all planets fit this pattern. In particular, warm Jupiters with a smaller companion interior to them likely did not undergo eccentric migration, because that would have thrown the smaller planet out of its orbit too. And TOI 1670 has exactly such a combination, and it's one of several stars that do. So that suggests there's an additional population that's not covered by the usual formation models. Here's another planet that's remarkable in large part because of where it is, TOI 1696b, a 3-Earth radius planet orbiting an M4 red dwarf in the Neptunian desert. The Neptunian desert is a region of the parameter space of exoplanets where there just aren't any planets, or very few. This is because planetary atmospheres evaporate if they're very close to their stars. For giant planets like hot Jupiters, they're massive enough that they hold onto their atmospheres. But something like a Neptune-sized planet, the atmosphere completely evaporates away, and you wind up with a rocky planet that's not much larger than Earth. And that region where you expect all the planets to have their atmospheres evaporated away is marked by the black lines on this plot. But there are a few planets within the Neptunian desert, including TOI 1696b, which is the blue point. And I should note that young planets can still appear in this desert because they still have their atmospheres, but TOI 1696 is an old system. In fact, older than our own solar system at about 8 billion years. So this is an interesting borderline case to what kinds of atmospheres exoplanets can have. The third discovery I thought was interesting is not technically a planet, but rather a cloud of dust produced by planet formation. In the HD 166191 system, in the potentially habitable zone, astronomers have found very deep transits of the star. In fact, transits that block out 80% of the star's light. A planet is not going to do that, but a large cloud of dust can do that. The cloud of dust would have to be about the size of the star itself, but that is certainly possible in planet formation. In fact, there are some stars where we have discovered what appear to be debris clouds from whole planets colliding, just like the giant impact that formed our moon. In this case, the dust cloud appears to be caused by the collision of planetesimals a few hundred kilometers in diameter. Because this is a very young system, only 10 million years old, so the planets are still forming. So this is a rare glimpse into the formation process that is more direct than we usually get just looking at gas disks. Now, besides the individual planets, there were a couple of interesting papers looking at planet populations. The first one is for the Hades RV program with the HARPS North spectrograph, looking at planet occurrence rates around early M-dwarfs, that is, red dwarfs. And this is important because red dwarfs are the most common type of star in our galaxy, but they're very hard to see, so we don't have great statistics of planets around them yet. This survey is trying to calculate the fraction of red dwarf stars that have planets with particular orbital periods on the left and particular masses on the right. The periods are all less than 100 days because longer periods need a longer baseline of the survey to detect them. The interesting thing you'll notice is that most red dwarf stars have mini Neptune or super Earth-sized planets less than 10 Earth masses, occurrence rate of about 1, but very few, less than 1/10, have even Neptune-sized gas giants, let alone Jupiter-sized ones. And this is simply because red dwarfs are small stars, and one thing we are pretty sure about is that they are more likely to have small planets, and much less likely to have large ones. So this is an important step to understanding the planet populations in our galaxy. But I thought the more interesting one was this survey for pulsar planets. As I said, the very first exoplanets that were confirmed to exist were planets orbiting the pulsar PSR B1257 plus 12. Those serial numbers are usually coordinates if you see a plus or minus in them. And these are weird objects. They're very small, around Earth size or even smaller. They probably formed from the supernova remnant. But even then, it's not clear how they formed because most pulsars do not have planets. And this study confirms that. They looked at 800 pulsars for timing variations. The gravitational pull of a planet will cause the pulsar to move in space slightly, and that can be detected in the timing of the radio pulses seen from Earth. And because the timing of pulsars is so incredibly precise, we can detect orbiting bodies down to large asteroid size around them. And at this point, about a dozen pulsars are confirmed to have planets, but that's still not very many. This study looked at 800 pulsars and did not find clear evidence for any other pulsar planets. The best candidate they found was for PSR J2007 plus 3120, shown by the peaks over the noise floor of essentially signal strength in the timing variations versus orbital period. But it's not a very clear detection, and the most likely is that it's just random noise and there's nothing there. So that confirms that pulsar planets are pretty rare occurrences. Moving on from detecting planets to characterizing them, we have another paper, 1 year of AU-MIC with HARPS 1, measuring the masses of the two transiting planets. AU-MIC, of course, refers to AU Microscopii, which is the nearest young star to our Sun. And by a great stroke of luck, because transits are not that common, AU-MIC has 2 transiting exoplanets. And these are maybe not the youngest planets, because we might be able to find some in nebulae, but certainly the youngest planets that are anywhere near that close to Earth. And they looked at radial velocities for AU-MIC and measured better masses for the planets. Not super precise, but it's a young flare star that's a little bit hard to get radial velocities from. and they measured them to a little over 10 and a little over 20 Earth masses. And of course, they combined those measurements with the transit radii, plotted them on our handy mass radius diagram, and also used atmospheric models to evolve them forward 5 billion years to mature planets, where the planets would be expected to fall on the diagram when they're the same age as Earth. And this indicates that both planets have significant hydrogen atmospheres. AU-McB seems to be maybe 2% hydrogen by mass, and AU-McC is about 1% hydrogen by mass, which is very typical for Neptune-sized planets, especially close to their stars. Another interesting result was carbon monoxide emission lines reveal an inverted atmosphere in the ultra-hot Jupiter WASP-33b and indicate an eastward hotspot. And this is a really interesting, and to me it's the inverted atmosphere that's more interesting, but it's a very interesting effort all around, which is for very hot planets, you can observe them going all the way around their stars and map their surfaces to a crude degree. How it works is, as a planet goes around its star, it has phases, just like our moon's phases or Mercury's and Venus's phases. And even though the star is much brighter than the planet, for hot Jupiters, they're still pretty bright compared with the star, and you can see those phases in the combined output of planet plus star. So you don't just get a transit shape, you get an entire orbit. And this team looked at the light curve over the full orbit for WASP-33b and detected an eastward hotspot. So the paper didn't provide a map, but if we look at the very similar planet WASP-121b, this gives an idea of what they would have seen. On top, we have the light curve with secondary eclipse. The sharp dip is where the planet goes behind the star, and its emitted infrared light is blocked. And the sinusoidal curve is from the planet's phases. And you'll notice the secondary eclipse is a little bit off-center. This is because normally we expect tidally locked planets to be hottest directly underneath the star. But tidally locked planets actually do rotate once per orbit, and if their orbit is only a few days, that's going to create quite a bit of circulation in the atmosphere. So the hottest part of the atmosphere is where the winds carry the heat from the substellar point a little bit to the east. But the more interesting part is that they detected emission lines instead of absorption lines. And emission lines happen when you have a hotter part of the atmosphere above a colder part. So they produce extra light on top of the regular spectrum. And it's not unusual to have a hotter part of the atmosphere on top of a colder part. Earth has two of them. In the stratosphere, temperature increases with altitude, and it increases again in the thermosphere. But we've been having a hard time seeing stuff like that in exoplanets, even though we expect it should happen. Well, WASP-33b shows carbon monoxide emission lines, which does indicate what we call an atmospheric inversion, where the upper part of the atmosphere is hotter. And here are some model temperature profiles based on the observations. And this hotter upper atmosphere is usually caused by some kind of infrared absorber. And for hot Jupiters, that tends to be titanium oxide, vanadium oxide, and even vaporized rock and iron. So that's a pretty cool find. And of course, we have to talk about the latest Hubble spectrum of TRAPPIST-1H from the famous TRAPPIST-1 system of planets. TRAPPIST-1 may host as many as 3 planets in the habitable zone. Planet H is not one of them. It is the coldest planet in the system at twice the habitable distance. It's also quite small, only a third the mass of Earth and 3/4 Earth's radius. So it's certainly a rocky planet. And if we could detect an atmosphere from it, that would be a big deal. So Hubble looked for one and completely flat, which is what we would generally expect. it is nearly impossible to detect transit spectra from low-mass planets because of either clouds or just, in this case, it's rocky planets, so the atmosphere is probably very thin and would have a small signature. We can only really detect hydrogen-dominated atmospheres with current technology, and many of those are blocked by clouds, but it's still a high-priority target, so it's good to have this spectrum in the database. Finally, we have the K2 and Spitzer phase curves of the rocky ultra-short-period planet K2-141b, which hint at a tenuous rock vapor atmosphere. I mentioned vaporized rock on hot Jupiters. In that case, it's not really vaporized rock, it's just vaporized iron and silicates that never got the chance to cool into rocks. But for an ultra-short-period rocky planet, that actually is vaporized rock. K2-141b was discovered by the Kepler Space Telescope in its K2 mission. It's an ultra-short-period planet with a year of just 7 hours, orbiting a type K5 star, and it has an estimated average temperature of 2,000 Kelvin, or 3,300 Kelvin on the day side. And just like WASP-33b, the team was looking at phase curves, the light signal over the orbit, marked by the black points on the graph. And that phase curve better matches a model with a thin rock vapor atmosphere versus a thicker atmosphere that transports heat more efficiently, or just no atmosphere, although it still could be no atmosphere. That's a little harder to detect. We've gotten a few hints of rock vapor atmospheres like this, and we're still trying to find definitive proof, but this is an important step. Moving on from characterization to theory, there were a couple of papers about mass loss, one about atmospheric escape from extremely close-in gaseous planets, and this one specifically looked at a process that affects only the very hottest planets, called Roche lobe overflow. Roche lobe overflow happens when you've got a planet or star that is orbiting a larger body, and its atmosphere is extended due to heat far enough that it's pulled out of its own gravitational field and into the companion star's gravitational field. So instead of being blown away by solar winds or ultraviolet heating, the atmosphere is stripped gravitationally. And they calculated this process compared with mass loss from ultraviolet-driven escape. They determined that if you have a Neptune-sized planet orbiting a sun-like star, this Roche lobe overflow will be the dominant mass loss process if its orbit is shorter than about 2 days. And if we go back to that Neptunian desert plot, 2 days is marked by the red line, and so we would expect the region to the left of that line to be especially empty of planets, and what do you know, it is. That's the only region where there's really nothing there. Another paper looked at smaller planets, indeed potentially habitable planets that would have liquid water and water vapor, and how their mass loss processes would be affected by orbiting a flare star. Many red dwarf stars produce much larger solar flares than our sun does, which means a lot more X-rays and ultraviolet light that can strip away the atmospheres of very close orbiting planets. And comparing the usual atmospheric escape processes to those that include these giant red dwarf flares, we see that the flares can strip away significantly more water, twice as much or even several times as much. And that would apply to the whole atmosphere as well. So that's an important process that needs to be taken into account when calculating the properties of planets. The third paper was looking at not mass loss from planets, but mass loss from stars. Specifically, what happens when a star becomes a red giant and potentially engulfs its planets. And this is about what it would look like. This is what we expect will happen to Mercury and Venus as our own sun ages. Probably not Earth, but we're not sure. Where the outer layers of the star expand to engulf the planet's orbit. Its a very, very thin gas, so the planet can actually orbit for a while inside the star. But there's enough gas to create drag, and that will eventually cause it to spiral into the core and disintegrate. But for a sufficiently massive planet, it could survive that passage. And instead, the planet's gravity could blow those outer layers off the star entirely, leaving a smaller star. So this team looked at how massive a planet would need to be to do that. Turns out it would need to be a brown dwarf, pretty much. Jupiter-sized planets, especially hot Jupiters, would disintegrate pretty quickly as the star ages. Warm Jupiters and warm super-Jupiters would last a bit longer, but would still disintegrate. And only brown dwarf-sized objects would be large enough to eject the envelope of the star instead and survive. And I thought this was an interesting result, because a few years ago I remembered seeing Kepler 70b and also 70c, which was a proposed planet orbiting very, very close to a post-red giant star called a sub-dwarf B star, which is essentially a red giant where the envelope has been ejected. This planet orbited in 6 hours and was reported to have a temperature of 7,500 Kelvin, and that is hot enough to vaporize any material known to science. It would have to be a gas ball, even if it was nominally made of rock. The trouble is, it was reported to be smaller than Earth, so it's hard to imagine how it could have survived the red giant phase of the star to wind up that close. But later research suggests that these two planets don't actually exist, and it was just stellar variability. And this theoretical model backs that up because it says nothing anywhere close to Earth size would be able to survive inside a red giant. So that's further evidence that these planets do not exist, but perhaps eroded cores of brown dwarfs orbiting very close to post-main sequence stars could exist. And finally, I've got one speculative paper that I wanted to look at. The case for technosignatures. Why they may be abundant, long-lived, highly detectable, and unambiguous. Now, technosignatures are detectable signs of alien technology, just as biosignatures are for biology. And this could be something like a Dyson sphere blocking out the light from its star in a recognizable pattern, or it could be communication lasers from the other side of the galaxy, but it could also be things that we produce ourselves, like radio and radar signals that aren't actually directed into space, or lights from cities, or even air pollution. And looking for technosignatures is one method people are using to try to find alien life. Now, to figure out how many technosignatures might be out there, the authors use a formula similar to the Drake equation, which essentially replaces the lifetime that a civilization exists and is able to communicate with the lifetime of the biosphere, where biosignatures can be detected, versus the lifetime of potential technosignatures. And they advocate for further work in detecting technosignatures, because we assume that there are more biosignatures out there than technosignatures, but that's not necessarily true. There are biosignatures on exactly one planet in our solar system, but there are technically technosignatures around 4 planets: Earth, Venus, Mars, and Jupiter. Those being the 4 that currently have active space missions producing radio signals. Very weak radio signals that almost certainly could not be detected across interstellar distances, but they are there. The authors say, we also normally assume that the lifetime of a biosphere is much longer than the lifetime of technosignatures, but that's not necessarily true either. We don't have a representative sample to determine that. And technosignatures, at the very least, could far outlast us as a civilization if we build some kind of megastructure or even just carpet the Sahara with solar panels, as Andy Weir suggests. And meanwhile, our own technosignatures that we're producing today would be just barely detectable with our next generation telescopes. And so the authors say these kinds of signs of alien life are definitely worth continued searching.